Well, is there anything you can do about that?
Okay, we're going live.
Okay.
Right.
Okay, we're live?
Yeah.
Okay.
You can see the chat too on another computer. Yeah. I'm starting off with this.
Okay. Okay, I'm not seeing anything of the YouTube studio channel.
What?
Should I be seeing the YouTube channel?
No.
Oh, okay. You're gonna deal with that, the chatting and everything?
Yes. Actually, unless you want to open the stream, but only look at the chat. Don't look at the video.
Only look at the chat. Okay.
Yeah, you have to mute the. You have to pause. You have to stop watching the stream, and you have to pause the video, and turn off the audio, or else it'll be background.
Okay. Turn off. Okay. Well, if you want to, if you can read the, are you going to be able to deal with the chat, or is that going to be too much? You want me to do it?
I think you should look at the chat.
Okay. All right. So then I'll need to turn off the audio on what? On YouTube?
Yeah, you can't watch the, because it's the
right.
thing I'm going to be showing you anyways.
Okay. Okay. Well, I will. Okay. So then we don't want to be sharing video screen, right? Just share audio then with the Zoom.
You're not supposed to touch anything with Zoom.
Sorry?
This has nothing to do with Zoom.
Okay, should I close Zoom or?
No, you shouldn't close Zoom.
Yeah.
That's how you're talking with me.
Right. Okay. So, oh, okay. You disabled the screen sharing. Okay.
You shouldn't be doing anything with Zoom. You should just be going to YouTube.
Okay, I will do that. So I'll minimize Zoom.
It should have started now.
Okay. Okay, yeah, we've got 5 people watching. Okay, well, welcome people. Nice sunny day, I believe, in San Marcos, so we'll be looking at the sun.
Your audio on YouTube isn't turned off. It's
oh, okay, let me do
back
that.
feeding.
Audio on YouTube isn't turned off.
Okay, it's off now. Okay, well, anyway, this is Doug Solacey in Loreto, Baja California South, and remotely with Vivek, who is in San Marcos, and he has 2 telescopes set up for solar viewing. So one is going to permit us to see the whole sun, and then the other one will give us a close-up look. So we're looking forward to having some chatting with you and to talk about the sun, its nature, its processes, what it is we're going to be seeing. All questions are good. So, okay. Okay, Vivek, why don't you tell us what kind of equipment you're using to show us the...
Well, the first piece of equipment right here is the same 5-inch 130 SLT from the cheap Deep Sky Star Party, and I've just hooked it with the camera to show the sun what it will normally look like. You can see the entire sun. You can see 3 sunspots on it, and this is just a white light view. And as you can see, the sun is white, so that's the one of the takeaways from here. It's not. Most people perceive it as yellow because of the atmosphere, or when they look at it really low, there's even more atmospheric scattering that occurs of blue light, so it looks a lot more yellow. But in fact, it's actually white.
Okay, what kind of filter did you have on this?
It's just a white light solar filter. So it's one of the same solar filters you get for eclipse glasses, or to put on the front aperture of telescopes, or so that kind of filter.
So Mylar.
Yeah.
Okay.
So it's just a very typical view of the sun in terms of what people will most experience with when they try to safely look at the sun.
Right, and this is over the aperture of the scope.
Yeah, it has to be over the aperture of the scope. There's no other place for a filter, and there was this plane. There's no other place for a filter only in like a few exceptions, but.
Did we just have a plane fly in front of the sun?
Yep.
Wow.
Wasn't recording though, so it doesn't matter.
Okay, all right, Roger, welcome back. Okay, so we just want to emphasize that safety is really important when we're talking about solar observation. Anyone who wants to try to use a telescope with the sun, you've got to put the right filter over the front of the scope, over the aperture. You don't want to try to filter it as the light and heat are concentrated and shooting down to the eyepiece. And like if you've ever seen someone with a magnifying glass burn hands or something like that, that's what it would do to your eyes. You don't want to mess around with that. If you're not sure what you're doing as far as observing the sun, just don't do anything. That's the best advice.
Yeah. And if you want to, if you buy solar, like eclipse glasses, you have to make sure they're actually attributed and they're not just cheap knockoffs, because those can actually damage your eyes.
Okay, so we're seeing some sunspots right now. How long have we been seeing sunspots lately?
For a good while now.
Okay, when you say a good while, what, you mean years or weeks or what?
Just weeks.
Weeks.
There's a very long period where we had no sunspots. That's so that's good news.
So we're in a new cycle then.
Yep.
This wouldn't have been worth doing 6 months ago, because we would have just seen a white disc with nothing hardly we could identify on it.
I'm gonna try to capture this now so we can stack it.
Okay.
But I have to capture a very small area, or else it's gonna take years to actually. So we're just gonna capture only a small segment of the sun.
Okay, I think we could probably guess which part you're going to capture.
Yeah, the one with sunspots.
And the purpose of capturing multiple images to get a sharper view.
Yep. The same stacking procedure we usually do for planets or the sun or the moon. We're gonna take a lot of frames, then stack them in software and output a image that requires a little bit of processing, but hopefully with a good result.
Okay.
Yeah. But on the other hand, after we're done with this scope, we're going to be moving on to the next. Are you still getting feedback from Doug?
Am I still getting feedback? No, I mean the background.
No. No, Roger Monroe's saying he's getting feedback.
Oh, okay. Yeah, Roger, are you still getting it? I don't hear it myself. I can turn my speakers down. It shouldn't be picking me. Okay. Okay, we're getting a few more people now. All right, so, okay, so basically the image processing method is the same as for night sky viewing.
Yep. Okay, so guess we'll start moving on to the other scope. So we got our view. That view of the sun is the photosphere. So it's just basically all you can see is sunspot and granulation, and not much more than that. But we'll be looking at a different view of the sun with different equipment that can show a lot more detail.
Okay, so that basically that view of the sun's with a low budget filter setup, right? The Mylar
Yeah.
filter is
Yeah.
kind of the least expensive way to go as far as solar viewing.
Yeah. And I'm currently gonna stack this, so
Okay.
surface. This might take a little bit long. This might take a while though. So let's move on.
How big would you say, like the largest sunspot there? Any rough idea of how big it is?
Well, it's gonna be multiple Earths, for sure.
Multiple Earths. Okay.
Yeah.
Okay.
now we've moved on.
seeing a little-
Now we've moved on to this. And if you notice, it looks a lot more. I mean, I guess I can zoom out, but it looks a little weird.
give-
Oh, this is interesting. Okay, let's.
So this is a close-up of the photosphere.
This is the chromosphere.
Chromosphere, okay. What's the difference between the photosphere and the chromosphere?
The chromosphere is above the photosphere.
Okay.
It's less bright, and you can only see it in certain conditions, such as what we're doing right now. So, very tricky thing to comparatively to try to observe. We're looking at it in a wavelength called hydrogen alpha, and that's one of the spectral lines of the sun. And if you look only within a very small range of that spectral line, you start seeing the chromosphere, which is a layer above the sun. You can see a lot of different things that you normally associate with the sun, such as prominences, all of these little granulation. There's a lot you can see with this, so we're going to try to take a look at it.
So can we talk, is there such a thing as something like the surface of the sun? Would that be the chromosphere, or is there?
Well, if you were talk about the surface of the sun, you'd talk about the photosphere.
Okay.
Just
So
slightly, this is above that layer.
Uh-huh.
And this is where you see all of the different phenomena, such as prominences and all of that sort. I mean, I guess we can try to take a look at if we can see some prominences. But I'll
Okay.
have
So is the chromosphere, is that where we see material being ejected from the sun?
Sure.
Okay.
Depends on how active the sun wants to be on that day.
Yeah.
So let's see if we can try to find prominences.
So when we talk about prominences, for people who aren't familiar with that term, those are, that's something that's shooting up way above the surface.
Yep.
Okay, so we're gonna be looking along the edge of the sun here.
Yeah. Let's see if we can try
Okay,
to
I
find any.
like seeing some prominences kind of down about, I guess about, 5 o'clock there. I was.
Try to look for one of the more brilliant ones. That might be this one. Yeah, it really depends. It's dependent on how the sun's feeling that day. See if there's any on top. Okay, well let's get. I guess this is the biggest one here. Let's try to zoom in on that. This is a very small prominence, I think.
So you would call that a small prominence?
Relatively, compared to what I usually try to go for. Or there.
Okay, so the people who don't know, the diameter of the sun is about 864,000 miles.
Yep.
So that maybe.
So if I lower this, yeah, if I lower the exposure, you can see this detail on the sun, all of this granulation. These are basically small convective cells that are basically turned in the sun, and that's because the basic structure of the sun is at the very core. You have hydrogen fusing into helium currently, and all of that heat all of the heat and light has to starting to escape. So they go up through these layers of the sun, and at the photosphere, you start to get these little granulation cells, and at the very top above them you have this chromosphere. You have this granulation, and it has a lot of different convective fibrils and all sorts of detail. And you have to remember, these are all plasma, so these are very hot ionized gas. And if we increase exposure, this prominences over here are basically that material getting expunged above the chromosphere by the magnetic fields of the sun, because very hot plasma generates very strong magnetic fields, and when you have this big giant ball of plasma that's convecting, you get a very scattered magnetic field. So you get all of these very interesting phenomena happening. Sunspots are a result of concentrated magnetic flux, and that starts to cool down that specific part of the sun. And prominences are caused by magnetic fields arching above and basically dragging around the material. So what you see here, right over here, is one of these prominences. Now, let me try to capture that. So this is through a regular 80mm refractor telescope, but I put a hydrogen alpha filter made for the sun behind it, and that allows you to see all of this detail.
Okay, prominence like that could appear would it be a process of days watching it appear, or would it be shorter time frame?
Hours.
Hours, okay.
Okay,
so within
actually,
hours, you could be observing the sun and see change happening within a single day of observation.
Yeah.
Okay, I think Dave Decker asked what type of filter you were using.
Yeah, well, I'm using just an 80mm refractor, but I have the hydrogen alpha filter that's called a Daystar Quark, and it's on a. So when I said that you always have to put when you have to put a front-mounted filter, there are some exceptions, and this one's included. There is no front-mounted filter here. It's just the 80mm refractor. At the bottom, there's a diagonal of the ultraviolet infrared cut to act as to basically reflect away all of the ultraviolet infrared, because that can be very damaging. And then you insert that hydrogen alpha filter, the cork, and then I put the camera at the top, back, and that allows you to see this.
Okay, so there's two different filters functioning.
Well, it's the UV IR cut is just for safety reasons. Because you don't want to have infrared and ultraviolet entering into the. At 80mm apertures, it's technically not necessary, but if you start to get if you start to collect more light, then it can start getting pretty nasty. So that's why people with around 80 to 120mm apertures on this type of filter, they use a UV IR cut, but above that, you have to start using a front-mounted filter to reject a lot of that light out. Okay, so this thing's done.
Okay, so what we're seeing on the surface, there's no nuclear fusion going on the surface. It's all
No, there's no nuclear fusion going on the surface. You're just seeing convection occurring. The fusion occurs only solely at the core. Okay, so I can now start stacking, and we should be able to get something. But yeah, okay, so that's the prominence. Now I guess I'll go back to the sunspots. Wait. I think it's over to the right. And then the prominences are much harder to see than the chromosphere, so I have to. So that's why it's much more faint. And then we're back to the disk of the sun. Got a sunspot there. I guess we can start with the sunspot. So just got a lone sunspot over here. Maybe I'll play with the focus. So we just got this lone sunspot over here, and if you notice around it, there's some bright regions at the bottom right. Those are called plages, and those are just regions of more active that are become more active as a result of the increased magnetic flux. The sunspot is just this phenomenon where the concentration of magnetic flux basically cools down that specific region, so it emits way less light than it would otherwise. So that's why they look much darker than compared to the rest of the surface.
And the area that's kind of peripheral to the sunspot is not quite as cool. Is that why it's gray rather than black?
Well, it's obvious it's going to be a gradient. It's not going to be immediate. It's not going to just be a place where all they don't really operate just like distinct lines. It's going to be a gradient. So we're just going to have this region that's slightly darker, and as you get closer to the center, there's more flux. There's going to be more darkening as a result. So I think, yeah, if you notice, the stacking does take quite a while. So we won't be seeing immediate results yet, but I can try to capture this now. If you notice, everything's in grayscale on this camera because hydrogen alpha is just one distinct wavelength, and that's best captured with the monochrome camera because the color sensor is not going to get data because it's just one wavelength. So, but usually when people image this, they colorize it later on. So that's something we'll do also. But the other camera that showed the white light image of the sun, that was in color. So.
So it was a color camera, but the white was light. I mean, the light was white. So that's why
it was white light.
Color.
Yeah.
So how long does it take for photons are produced as a product of the nuclear fusion going on in the core? So how long does it take for the photons to get from the core of the sun until they leave the sun and start?
A very long time, hundreds of thousands to millions. It depends on the path the photon takes, but it's a very long course. So, I mean, yeah, a lot of people love to point out how old the light is that we're getting right now on the sun. So.
You said hundreds of thousands of what?
Years.
Years. Okay.
It takes a long while because there's just a lot of matter. There's a lot of hydrogen sitting there, so the photon keeps bouncing back and forth, and progress takes quite a while until it breaks free of the sun. So
they're not going to be traveling in a straight line from the core.
No, it's not going to be a straight line. It's going to be it's going to be very slow progress.
So kind of like a pinball machine, they're bouncing around.
Well, a pinball machine, but taken to the extreme.
Yeah, pinball to an exponential pinball. Okay.
Yeah, the seeing isn't that great today, but that's okay. It's a little blurry.
So the seeming like fluxing under the image is that's just the Earth's
That's atmosphere. Yep, atmospheric distortion.
Right.
Okay, we got frames. I guess we'll move on to the next pair. I think they're bottom right of this one. Oh, they're right there. Next. Let me try to refocus. I don't know, it's blinking in and out.
So when was the chromosphere first observed? When did that happen as far as the development of science? You know?
That's not that old. It's fairly recent because it takes a while for that kind of stuff to happen. I mean, the first thing is people observe the spectrum of the sun. So that happened with Fraunhofer in the late 18th century, and then after that, people started getting better materials that'll observe that part of the sun, and then so they start observing and check more lines, and they look at them and try to identify what elements are in the sun. And then after that, they discovered an unknown line somewhere near sodium, the sodium doublet, and they decided to name that helium because, well, the Greek word for the sun is helios. And then those lines are very important because that's how you observe the chromosphere. Because when you just look at the sun, straight white light, which has been done for a very long while, you just see the sunspots. You don't see all of this type of this very distinct granulation. You see, if you have to take a lot of good seeing and very high resolution to see the granulation white light, but it's fairly easy to pick up in these wavelengths. So they have to start trying to observe specifically in these spectral lines the hydrogen alpha, calcium K, sodium doublet, magnesium. There's a lot of all of the Fraunhofer lines, which we covered before, and so that didn't really happen until the 20th century, and then after that, you can studying the sun becomes a lot easier, and then now a lot of solar research is done all across the electromagnetic spectrum, anywhere from radio to very, very commonly in ultraviolet, because there's a lot of different things you can observe in ultraviolet, and then in these wavelengths, in the titanium dioxide, I think it was, yeah, in the infrared. So there's a whole lot of ways people observe the sun currently. Yeah, amateurs have gotten their hands on this recently too. So the main barrier with this is it's extremely expensive to do hydrogen alpha. The filters themselves have to be high precision filters. So they have to be very small bandwidth. They have to show only a small sliver of wavelengths to really get this contrast and detail. So that takes a lot of engineering, a lot of money. So that's the most least expensive offering they have for hydrogen alpha observing is right now the PST, the Coronado Personal Solar Telescope. That's a hydrogen alpha telescope, which Doug had, but we were planning to use for the star party, but we ran into some hitches. But yeah.
Okay, so the sun is only producing helium.
Well,
Correct.
right now it's most of the fusion occurring with hydrogen to helium. So if you give it enough time, that'll start. If you give it a few billion years, that'll start to change.
Okay, when it starts running low on hydrogen.
Yeah, I mean, you're gonna have the interactions happen earlier too. It's not like it's all clean and clean, but majority right now it's very the big majority right now is just hydrogen fusing into helium.
But where are the other elements that are present in the sun? If the sun's not producing anything but helium, where do those other elements come from?
The sun was created with them, so these are from the remnants of other stars. So a lot of the calcium, the sodium, the lithium, almost every single element you'll see on the solar spectrum, most of those are going to be coming from when another star went supernova or became a planetary nebula, spread its the elements it created through nucleosynthesis, and found its way into the interstellar cloud that formed the sun. So, yeah, so the thing is, a lot of the fusion's happening in the core. So any elements that are created in the core, they're gonna stay in the core most of the time. So, for the elemental composition of the chromosphere, the photosphere, the layers we're looking at, they're gonna stay fairly constant for now. So it's not like you can start creating carbon. You can start creating carbon and oxygen that leak to the core, with the exception of being carbon stars, which is why they're very strange. But
So the other elements that are in our solar system were part of the solar system disk.
yeah,
Gas and dust. They came from material that existed before the sun,
yeah.
from previous generations of stars.
Yeah, I feel like this is gonna take way too long. Let me try something else. Hopefully this doesn't take too long to stack. Yeah, the stacking the sun takes a long while. Okay. I mean, I guess I have examples of what these type of photos can look like after you're done with processing and all of that. Yeah, let the animation start up. There we are. This also happens to be the thumbnail, so.
Oh boy.
But yeah, this is a span. This is only like 1 to 2 hours worth of animation. So what you're seeing here is the basically we're taking the video. We're taking a lot of these videos, stacking them, and then stringing together an animation that really shows you quite distinctly how much activity is occurring on the sun. So.
What was the time period that these images were taken?
1 to 2 hours.
Okay, so we're seeing activity
It's
changed visually or visibly in 1 or 2 hours.
Yeah, this happens very quickly. So we can see the prominences here, they're really changing. You can see that if this is the influence of magnetic fields. You can see all of this surface granulation, it's extremely sporadic and active, and you can see all of this plasma moving around. And there's this little sunspot in this corner. Then this one. Let it load. So you can, this prominence looks kind of like a tornado. You have the sunspots here. You can see, I think it's loading now. Yeah, it loaded. Okay, so you have all of these, oh yeah, there we go. That's much better. So, yeah, this GIF is pretty big. It's since this is a really big part of the sun and it's looping an animation, it's like 200 megabytes. But yeah, you can see how active the sun is. You have a prominence here. You can see material getting expelled from the chromosphere. You can see the sunspots and how there's just all sorts of activity going on here. You have the prominences. This one looks kind of like a tornado. See how a lot of this plasma is streaming around. So yeah, and if you take solar animations, it really shows how dynamic the sun is. If you notice how this part of the sun, this ridge over here, kind of looks like it's coming up, that's because this is also showing the rotation of the sun itself. Because the sun is rotating, and it's rotating, and it actually depends on latitude because it's not a solid body. It's a big ball of plasma. So different parts of the sun have different rotation periods.
So a major event of ejection that would cause disruption of communications, say, on Earth, would we see a prominence? Would that be something that we would actually be able to observe and forewarn?
A prominence is not going to be any harm to anyone.
Mm-hmm.
What people are more worried about is coronal mass ejections, which usually result from a solar flare. So the solar flare is not this. This is a prominence. A solar flare it's an event. It happens when you have a very big increase of activity in an active region of the sun. So these are what you'd call active regions because activity is there. You see sunspots, you see these plages, which are these little bright areas. You see all the prominences associated with them. So what happens is it's an event where this starts becoming really active, and what that can do is it can eject material from the corona, which is basically the layer above the chromosphere. It's what you see during a solar eclipse, the coronal streamers and all of that detail. That material is full of ions, and that can get ejected out of the sun in a particular direction. And if that's headed towards Earth, that can cause a lot of disruption. So That's what a solar flare is. It's not a prominence. These are called prominences. So, but yeah, that's what people are usually worried about because those ions can interfere with radio communications and anything that happens to be electronic or electromagnetic. So that's the big worry.
So would a solar flare, would we visually be able to notice a solar flare happening?
Well, what happens is, like, say a particular part of the sun, it starts emitting a lot of light. So if you look at the photos of a solar flare in the sun, what you see is basically just one little point of light, and it looks extremely bright. So it looks like it's kind of like a star. It's outshining the region, and that's what a solar flare event would be. It's not a prominence. Let's make that clear.
It's going to look very different than prominence.
Yeah. It's just one part of this gets really bright, and it's like if you think of like a supernova outshining its galaxy, it's kind of like that, except it doesn't outshine the sun, obviously, but it's like this one point that gets really bright. That's what it looks like. And all of this activity gets even more ridiculous. So these Pleiades become brighter, you start to get material swirling around, and the coronal mass ejection can happen. And that coronal mass ejection is the part that people get worried about.
We can see just from watching prominences, though, the turbulent character of the sun, that it's not a smooth glowing ball.
Just don't get worried about prominences. They're just something pretty to look at.
Yeah.
They happen all the time. Technically, solar flares happen all the time, but there's classes of solar flare. So there's that you can have. So there's the really aggressive ones are like X 9.3 or something like that, and less aggressive ones have a less scary denotation. So. But right now the sun is in a solar minimum. So the sun has an 11-year solar cycle, and and right now we're supposed to be leaving the minimum, and that's why we're starting to see some uptick in activity. So, and then given like 5.5 years, you might see the peak of activity, but we don't know how strong that peak will be.
Okay, so then we'll be seeing more prominences as well as sunspots.
Yeah, we'll see a lot more activity. We'll see a lot of more features. It will be really interesting for people to image. That also depends on the degree of activity. So we don't know how much the sun will give us, but we can hope.
What scientifically, are there more learning that can take place when the sun is more active?
Well, it's very interesting to see the sun active. So there's a lot of research you can do when it's active. But I mean, another effect of it is because there'll be more material coming from the sun. So the solar minimum and maximum, they actually affect how much orbital friction there is on satellites, and because atmosphere wanes and waxes depending on the solar cycle. So that's another effect. So the sun has the sun, I mean, since it's the source of a lot of our energy and it's what keeps us alive, it has an enormous influence on almost everything.
So the solar wind has changed. It changes along with the cycle.
Yeah. Let's see. Yeah. There's. Let's see how that. We can see how that. Let's see if how that prominence is doing over there. Is that the only one there? Yeah, we just got one lonely prominence for today. Yeah, but this by now this shape will be completely different than how we captured it. It's because it's always dynamic.
Oh yeah, there it is down the lower left.
Okay, this is gonna take a while. Okay, it's taking way too long, so I might have to just take a smaller region much more quicker so it can stack. It also doesn't help that it's hot outside. The CPU doesn't like that.
Yeah.
So I'll just take a very quick video so like that'll be able to stack quickly, so we can start looking at some stuff. Hunting for the sunspot. There we are. Just take a very quick 30 seconds of it. Should be enough. This is for the sanity of the CPU.
It's kind of interesting. The last star party, we were looking at the moon, and the apparent size of the moon and the sun are about the same.
Yeah, it's a coincidence.
Mm-hmm.
And that's the coincidence that gives us total solar eclipses.
Yeah, at least until the moon gets further away from the Earth. We won't get total.
Okay.
We'll get annular eclipses.
We got a much better animation, much better video. Maybe this one will stack now. We don't need that. Okay, that's fine. Hopefully that's faster. We can start processing. Oh, I did check it. Great. Oh, I think it's RGB. It's not. I guess that's why.
I think one thing that's helpful to realize when you're looking at the sun that we're seeing, like, something that's the same kind of image scale like the moon, but the moon is 240,000 miles away and the sun is 93 million miles away. So
Or 144 million kilometers for sane units.
So the details that we're seeing are enormous compared to the details.
Oh yeah, this is probably like like 1 or 2 Earths right here. This sunspot's around 1 or 2 Earths big. That's how big this is. So imagine this planet of ours, but that's what you're seeing right here. Very.
In other words, something that's 15 or 20,000 miles across.
Okay, there's nothing in the chat right now, so yeah, this is even on a 30-second video. This is a very slow process. Yeah, usually when I have a whole sequence of large videos, it's like 180 gigabytes. That takes like half the data stack. That's how enormous this stuff is.
By the way, people, just because I'm asking questions doesn't mean you shouldn't be. So, please feel free to fire some questions at us or comments in the chat.
Okay, 28, 99. It's getting windy now. Yeah, this is slow. Let me see if there's anything else on the sun right now. Okay. Is that the only prominence? It was much better yesterday. That's too bright. Okay. Now we can see most of the disk. Should give us an idea. Oh, there's something there! Okay, finally. Right. Some new prominences. There's the chromospheric part of it. There's a chromosphere. You can see a lot of the granulation there. And if we increase it, there's the prominences.
Oh yeah, over on the other side.
But yeah, this detail in between, let's see if I can expose it. This detail of this layer over here, these are spicules, so these are little tiny little streamers that you can see just barely above the surface. Over here, in that border. And then after that you can start seeing the prominences. But they're right now not ejecting anything in space, they're just sitting there. So, not quite dynamic over there. Oh, finally. Good. Okay, stack. Oh, this is taking... Oh, that's quick. Alright. Is it done? No. Yeah. Alright. There's quite a lot of atmospheric distortion. Really, let's see. Oh, it's almost done.
Well, that's definitely still a pretty nice amount of detail.
That's just 30 seconds, and it's taking, that took like 5 minutes to do.
Mm-hmm. It's definitely giving a lot sharper detail. So there, right now, there's was it the Parker solar probe?
Yeah, that's right now.
How close is that to the sun?
Very. It's 3 million miles, I think.
3 million miles from the
Approach.
sun.
I don't know where it is right now, but at closest approach, I think it's supposed to be around there.
Mm-hmm.
Okay, it's stacked. Now we can finally do something with it. It's actually not. Okay. first stack. Probably our only stack. Alright, so this is what the magic is. Alright, let's apply that to this entire thing. There we are. That's much better. Okay, now this is sharpening. This is using techniques called deconvolution and sharp masking. So deconvolution basically reveals all of this detail. It allows us to get through this atmospheric turbulence and get the fine detail. And then this sharpening is just to make it more clear, so you can see it much more easily. But yeah, now we can start to see a lot of the details. So we see this small granulation around the sunspot. The sunspot's it's not completely circular. You got this interesting shape to it. I don't know.
Oh, yeah, that's...
You can see these streamers flowing away. I think these are fibrils, and then you can see all of this granulation all across the image. So this is what a sunspot looks like really up close. So, but they do it to.
Those are like the magnetic field lines, kind of like anyone's ever had like iron filings around a magnet. You get patterns like that.
Yeah, I mean it's because it is magnetically driven. Yeah. Now we can get to the processing.
Well, that's really nice detail now.
Doug, are you still looking at the YouTube?
Yeah.
You can look at the zoom. Okay, let's run that.
Okay.
That's how you colorize it.
Oh, okay.
That's colorized. Now you can get beautiful. Now you've got this. Now you've got the beautiful orange you see in solar images, and technically hydrogen alpha is supposed to be ruby red, but you can have artistic license. And now you can see, yeah, now you've got all the fine detail over there, and that's image of the current sunspot, one of the current sunspots there, taken during this. So, yeah, there's a lot of fine detail over here. Yeah, these cropped out artifacts are just because, you know, I wasn't perfectly trained on the sunspot, so there's going to be a lot of. So these edges are just basically artifacting from the sharpening, but yeah.
Well, the dark center is where the strongest magnetic, that's what the center of.
That's where you have a concentration of magnetic flux.
And what causes there to be a strong area?
Okay. Dave asked, what are you using for image processing? So the sharpening I did is in something made for specifically solar imaging. It's called IMPPG, but it's using basically standard methods like deconvolution and masking, and then doing the colorization in PixInsight, so to get the color on so it looks less grayscale. And let me ask you another question: are all suns like that? Well, a lot of them have sunspots, and you can actually detect them through spectroscopy. So, or through photometry, because sunspots can dim. So as the star is rotating, they can actually dim. So you can see sunspots in the light curve. And that kind of poses a problem for exoplanet people because, you know, because they use transit photometry, they're looking at how the planet dips the sun, but sunspots can interfere with that. So yeah, there's other suns have sunspots. And you can also detect them spectroscopically, and you can even measure them, because the magnetic field, it has an influence on the spectrum. So you can see that, and that's how they can even measure sunspots on other suns using spectroscopy. And but other but yeah, all of the stars have the same kind of differentiation of layers. You have this chromosphere, you have the photosphere, and you have the core. And so yeah, a lot of the suns look like this. But in terms of color, the sun's white, but other stars are obviously different colors. You have blue, you have more blue colored ones, you have much more darker red ones, you have white, yellow, that kind of deal. Yeah. What we're gonna ask Doug?
Sorry?
You were talking about the sunspot.
Oh, well, I was just, I mean, this is kind of a more general thought, but when we were looking at the moon, the last star party, someone who's never seen it before through a telescope said, wow, it has a lot of pimples. And I think that was kind of a reaction to maybe, an idea that bodies in space, cosmos, are all kind of even, smooth. There's sort of an idea, maybe there's some perfection or something out there. I think when you look at any of them, you start to see that there's irregularity. I guess that's what we're seeing with the sun.
Okay, let me. Yeah. I'm gonna try to take a quick exposure. I'm gonna take the same deal, try to quickly get this captured, so with the least amount of stacking time. 400. Let's get that. Let's see. Yeah, the sun is very detailed, and in white light you can actually see some detail if you have it good enough seeing and you really zoom in. But a lot of the detail it really looks a lot better with the spectral lines, because you see a lot more. You got to see a whole lot more detail and more events occurring. So that's why people tend to. Let me take 15 seconds. Hopefully that.
You're going to try to give us a sharper view of the prominences?
You can't see the prominences in white light. You can't see them. You can only see them with spectral lines. In white light, they're not part of the photosphere. So when you look at it in white light, they're not there. So if you want to see the prominences, you have to look at it in hydrogen alpha on a different kind of spectral line. Otherwise, you can't see that. It's only visible in that specific filter.
Is that because they're obviously they're hydrogen, but that they're not as bright as the solar disk that we're seeing?
It's because they're not part of the photosphere, so you won't see them in white light. They're a completely different layer of the sun. So they won't be visible there. Oh, that's quicker. Yeah, got that stacked. Let's open that up. I don't know if people can see that, but you can see that prominence there. Let me just process it up. Save that. Colorize that. and it's a little harder to see, so. Okay, now you can see that prominence more visibly. Yeah, there we are. There's not a lot of detail because the seeing isn't that good, but yeah, there we go. That's the photo prominence.
Wow.
Yeah. I mean, to get this kind of animation, there's a lot more processing and more intricate processing involved, but same idea.
Yeah. Well, Vivek is doing this on the fly, so
Yeah.
so it can happen in a reasonably short amount of time. But a lot of the images that he produces take hours of imaging and processing.
Yeah, like I said, it takes like half the day to stack for an actual. And then. Okay. Let me try to quickly before we end. Let me try to the white light image. I'll zoom in, do the same procedure, so we can get that quickly stacked instead of taking like hours. I think it's lost the sun, so.
Okay, well, we're waiting. I'll just mention that if anybody, this is the first time for anyone who's watching, being, participating in one of our virtual astronomy events, if you want to be in touch for future ones, just subscribe, which is free. You can do it on the channel. You just click the subscribe button. That's about all there is to it. Also, you can get on our mailing, our email list, do it in darkskynetwork@gmail.com, and we will send out a notification to you whenever we're doing any kind of event. Or there's something major important happening regarding dark sky preservation, celestial events, and we also have a great Facebook group, official Julian Dark Sky Network, and we get a lot of interesting postings that kind of tell you what's up in the sky, and also what's going on too in terms of scientific discoveries.
Okay, there we go. Got all 2 sunspots in 15 seconds. So now it can hopefully it actually stacks that.
Okay, Mike McKeague is with us. What I take it is probably in Regular Springs right now.
You have, Doug, you have a feedback.
Okay, well, I'll turn down.
Yeah, let's, so that stacks in like a few seconds.
Is that better?
Yeah, it's stacked. Almost there. Yeah, this is the last thing I'm doing. I think we've covered most of the activity that's there right now. Yeah, this is we're back to the white light, but as you can see, it's not a whole lot more to see compared to what you can see in, wait, let me pull that back. What you'll see with hydrogen alpha. So we'll have that for comparison. Stack. Yeah. 15 seconds is still taking a little bit of time. I think it's probably because it's color. So it has quite more information to do. Handle. Okay. That's over. So we can drag it in here. Alright. Yeah, that's a little bit... Okay, it's a little bit too strong. You can see there's granulation here, but it's just the sunspot and a little bit more. But it's there. You can also colorize this, of course, but I mean, it is white. Yeah. Hey, it's the same little shape for that sunspot as it looks in with hydrogen alpha, just a little bit, just flip. Yeah. Yeah, white light's really good for if you want to look at the sunspots, but I mean, the best detail will be in hydrogen alpha. Yeah. Are you still there?
Mm-hmm.
Yeah. So. Yeah. I mean.
And you can even observe sunspots with just a pinhole in a cardboard or something and project.
Well,
that
okay, that's better for like the eclipses. If you want to see these sunspots, because they're fairly tiny, so like the pinhole projection method, it has to be for when the sunspots get really big, which could be
Yeah.
years. But I mean probably the cheapest way of seeing these sunspots is trying to do solar projection with binoculars. So you point the binoculars at the sun, but you make sure you're not looking through them. You have to project them onto a piece of paper or wood, and so you can project the image of the sun, and there you can see the little details. It'll be in white light. It'll be the photosphere, but it'll be there. But yeah, that's so what you're really seeing here is you start to see a lot more of the activity with the granulation, but in white light you see basically the photosphere. So that's the difference here. You're seeing a completely different layer, and this is a layer where the sunspots reside, and then we can see the chromosphere just above. This part over here is the chromosphere just above that photosphere. So you're kind of seeing two different layers. You're seeing two different layers of the sun with both of these images.
So what's the depth of the chromosphere?
The chromosphere is like the upper atmosphere of the sun. It's few hundred kilometers a few hundred kilometers above the photosphere.
Mm-hmm.
But the photosphere is much more down there. I mean, the thing about a lot of these solar layers is that they're more like gradients than there are actually like defined lines. So.
Yeah, there's not a sharp division,
but it's sharp enough so where you see this, it's completely different from what you're seeing over here. But the chromosphere itself, you're seeing different things. So this is the hydrogen alpha. This is the hydrogen in the chromosphere, which is technically most of it. But you can also see the calcium in the chromosphere. You can see the magnesium. Those will show you different events, different activity, different parts that are going on. And that's what some people use as tracers for certain events. And when you're actually looking at other stars, spectroscopy. So what this image here shows is where the hydrogen is. So that's the hydrogen alpha solar filter. But calcium, magnesium, sodium, those will show you what those elements are and what those things signify. So like calcium, sodium, it looks a little more like white light, but they show you different parts of the chromosphere and the different elements. So there's a whole lot to observe on the sun. It's just not. It just gets a little pricey. Okay. Okay, I think that concludes the
Okay,
session.
anybody have any questions before we sign off or comments? This would be a chance to throw an interesting question out if you have one. Something that you've been puzzling over. Okay. All right, well, I want to thank VBEC for setting all this up, making this available to us. It's two telescopes, two mounts, and two cameras, and a whole lot of preparation. And we'll be in touch and let you know when our next event will be. We may not be having events as frequently as we have because we're getting into the winter months when the weather becomes
we're already starting to notice because the seeing is getting horrible.
Yeah. Yeah, well, that's a fact, not just a cloud cover, we're seeing too.
Yeah, it's completely clear. Okay.
Okay, well, anyway, thanks everybody for joining in with us, and encourage you to look up, see what's going on in the world of astronomy and science. One source I would suggest is Earth Sky News. They've been putting out a daily email newsletter for years, and always really interesting things, including solar activity, meteor showers, planetary conjunctions, and just some general knowledge of how to enjoy the night sky. So that's just a recommendation. Learning more about the cosmos and what's observable for ordinary people, what all the scientists are seeing, and we try to absorb what we know from a variety of sources and share it with everyone. So, thank you, and be in touch. Keep looking up.
All right, we can't say good night, but good afternoon.
Yeah, good afternoon. Okay. Have a great weekend.